Before I start my today's session, I must say that I have to put a cautionary statement. First of all, what is that cautionary statement? The cautionary statement is that when I started linear algebra, module 4, I referred a book to you uh, by Friedberg. A concrete, complete book was there in front of you. But in case of calculus, I have not referred any book, but I have split one of the chapters from a particular book, and that book, that chapter has been posted in the Google Classroom. Calculus is so huge that I think that you are already overburdened with Friedberg, so I don't want to put extra load on you. But whoever wants to get to know the actual book from which the chapter has been splitted, he can ask me that what is that particular book, and I'm going to refer that book to him. But the book is, most of your friends know what book I'm referring, and since I'm actually considering that book for studying module 2, I have to name the book officially, so that if you find time and if you get hold of the book, or if you want to download the book from Library Genesis, then you can download and you can keep it with you. Okay, the book's name is Introduction to Real Analysis by Bartley and Sherbart. Introduction to Real Analysis by Bartley and Sherbart. You can ask your CR. Probably she has the book with her, but don't think that I have given her the book, because she was having the book from the very beginning. And when I uploaded the chapter, she immediately asked me, "Sir, are you referring us Bartley and Sherbart to study calculus?" So I said, I'm not referring Bartley and Sherbart. I'm referring a particular chapter, but you can study if you want. Okay, so with this cautionary statement, I'm going to start my today's discussion. And you may ask me that why this is a cautionary statement. Why are you saying repeatedly saying that it is a cautionary statement? It's because we are actually, we are studying mean value theorem, we are at in the chapter of 7 or 6. Okay, chapter 6. Okay, and in chapter 6, many to discuss the theorem and the problems, many previously proved theorems and previously discussed definitions have been used. Okay, so many things were used over there. So if you read the chapter, probably you have read the chapter and you have come across that several terms are there which you don't know, that this is the meaning of the term. Say for example, neighborhood. So therefore, actually these sub chapters are actually dependent upon their predecessors, and since the predecessors have not been posted, I mean, intentionally have not been posted. So you may find a little bit difficulty in going through that particular topic of mean value theorem from this book. And if you ask me that why are you suggesting that book to me, that book to us, you can have we can have another book to study calculus or this mean value theorem. So many books are there. Okay, it's my duty to refer you a good book, but other good books are also there. But whatever good book I refer, the same problem will happen, that mean value theorem is not the first chapter of the book, and that it is actually in either fourth chapter or fifth chapter or sixth chapter. And while discussing that, many preliminary ideas regarding definitions, cluster points, neighborhoods, these definitions are actually required, and therefore the same problem will happen. So here you need a little bit of guidance from my end to make you acquainted with how to study real analysis. The study of analysis and study of algebra is, the style are totally different. Okay, so the approaches are different. Analysis is a bit too difficult, and you may not find the solution immediately. Okay, so we will try to stick to a domain of questions which have already been solved either by the book or by me. Okay, but if you want to venture into a territory where unsolved problems are there, then you have to dedicate a bit amount of time. And if you can do it by yourself, all is excellent. But if you cannot, you can give me, but you have to wait for me to solve, because I immediately, but many questions are there whose immediate solutions are not available. And I'm not in the habit of seeing stack exchange for finding solution. Okay, because it actually kills the pace, it actually kills the, I mean, enthusiasm towards a particular problem. Okay, and stack exchange, in stack exchange, I'm repeatedly saying, is a kind of organizer. Many solutions may be there, but the solutions pattern are actually wrong. Okay, but you can ask me this, we have a very few time for studying, because studying a particular subject, because we have many subjects at a time, we have to study many subjects at a time. So you are suggesting, we are not actually here to be a mathematician, we are here to be to study computer science engineering. So why to dedicate so many time in thinking a particular problem? So what is wrong if we go, if you see something from stack exchange? Now, to see solution from a particular source, there are two ways. You can see the entire solution, you can copy it and you can vomit, or you can get a hint of how they have done it. Okay, so there are two strategies. So if you want to see stack exchange, see, but try to get the hint and try to do it by your own style. With these discussions, I'm going to start my today's topic on calculus, mean value theorem. But before I start mean value theorem, some things we must discuss and we have to be familiar with. So let's start with definition of neighborhood. So let's write the definition: neighborhood of point. Neighborhood of a point. And here in this analysis, we are confined in the domain of real numbers. So let us write here real analysis. Okay, real analysis. So there is no provision of discussing complex numbers over here. Okay, everything is real. Everything will be defined in real line. So let us define a neighborhood of a point, and you write the definition in your copy also. Understanding is also required. So let us write the definition. Let small a belonging to R. R is the set of real numbers. It is the set of real numbers. Okay. We don't write R in this manner or in this manner, because this R and this R is always usually used to define relations kind of thing. So we actually use this type of R. Okay, alphabets can be written in a different way. So this is the way for which has been selected to define sets, to denote sets. Let A belonging to R and epsilon greater than 0. Then the epsilon neighborhood then the epsilon neighborhood of the point A is the set capital V, or sometimes you want to write it explicitly, you can write it as V of A suffix epsilon. Why epsilon is in the suffix, I shall explain. It is the set which is a collection of points, real points, such that the absolute value of this difference x minus a is less than epsilon. Such a point is called, such a set is called a neighborhood, epsilon neighborhood. This is not E, this is epsilon. I have to write it properly. Okay, this is the actual symbol. Now, what is epsilon neighborhood actually? It is very, the definition you can see is very abstract. So probably you are not getting it, or probably you are getting it, but let me tell you that this abstract definition you have to understand if you want to understand the calculus written in these chapters of the book. Now let me explain this neighborhood uh, concept with you. Okay, so epsilon neighborhood. Now what is being done over here? A point. What? Let me draw the real line. This is the real line, and from this real line we have selected a point small a. Okay, this small a is maybe positive point or maybe negative point. It doesn't matter. So this point has been selected, and you have chosen a number epsilon greater than 0. What is that number epsilon? Let us choose epsilon to be 1. Okay, I am choosing epsilon to be 1. Now epsilon neighborhood of the point A is denoted by V epsilon. So in my case, that neighborhood of A with epsilon equal to 1 it will be denoted by V1A, and it would be the collection of all such points in R such that this happens. Okay, so what is this actually? What is mod of x minus a? So in real analysis, whenever 2 points are given to us, this is a point x and this is a point a, and we want to find the distance between the 2 points, then we actually use the absolute value and we write the distance between the 2 points is x minus a. Okay, mod of x minus a. And what is the definition of mod x? Let me recall that mod x is equal to x when x greater than 0, mod x equal to 0 when x equal to 0, and mod x equal to minus x when x less than 0. We have come across this when we were in school. Okay, and why this epsilon is positive? Because epsilon actually is the measure of I mean it's the measurement of the distance. Okay, so it counts distance, so this distance cannot be negative, and therefore it is always positive. It is strictly positive. Why they haven't written epsilon equal to 0? So if epsilon equal to 0, that means so no distance is being counted between the points, then actually there is no point in defining neighborhood. If you are not taking any distance, then it is not, I mean, meaningful to study neighborhood of a particular point. So for neighborhood of a particular point, we need to have a distance which is non-zero. So therefore epsilon is positive, and not only positive, it is strictly positive. A is any real number, but they have not said whether they have considered positive real or negative real. So therefore we can consider 0 on the right hand side of A or 0 on the left hand side of A, whatever. And this epsilon neighborhood means that if it denotes it is containing those points of the set whose distance from A is less than epsilon. I mean, now one thing, suppose another student is choosing the epsilon to be 2, then in this case he is going to get a set of points like this. And suppose another student is saying, say he's, for his case, he is choosing epsilon in this manner. So in his case, his epsilon neighborhood will be like this: mod of x minus a 0.00001. Okay, and you see, uh, you know from real analysis that mod of x minus a epsilon, this can be written as this is same as minus epsilon less than x minus a less than epsilon, and this is same as a minus epsilon less than x less than a plus epsilon. Okay, so actually these things are actually equivalent to one another. This statement and that statement are equivalent to one another. So actually what is happening, uh, for your case, you are choosing a point, say a minus 1 over here, a minus 1, and a point a plus 1 over here, and you are actually uh, considering this interval. Another person is choosing a point a minus 2 over here, and another point a plus 2 over here, and he is choosing that interval. Another person is choosing a point uh, a minus 0.00001 over here, and a plus 0.000 over here, and he is choosing that interval. And there is no restriction in choosing epsilon. You can choose epsilon as small as it can be. And the neighborhood concept is actually a limiting concept type of thing, because you are choosing a value for the epsilon, but the distance is being counted and is being considered, the distance, so that it is actually less than your chosen value of epsilon. If your epsilon is too small, the distance between the points is more smaller than that. So therefore, this definition is actually very much, this definition actually becomes too helpful in studying the limit of a function also. The epsilon neighborhood of a particular point is very important concept in calculus. The second part is actually a theorem, and it is also very important. You have to know this theorem. It says that let a belonging to R is any point, a is any point in R, if x belongs to, if x belongs to the neighborhood, x belongs to the neighborhood, if x belongs to the neighborhood v epsilon of a, for every epsilon greater than 0, for every epsilon greater than 0, then it's a very important theorem, then x is equal to a, x is equal to a. I'm not showing you any proof of this and theorem, because just it will just kill time. What is being said? So once we have the concept of epsilon neighborhood, now you are choosing arbitrarily your epsilon, and for the point a belonging to R, and whenever you are choosing this point a, and its corresponding epsilon, whatever value of the epsilon you are choosing, you are always finding that if we, for a arbitrary, x is very arbitrary point, and whatever epsilon you choose, you find that this x is actually, this particular point x is actually belongs to that neighborhood of a. One such point x is there, one such point x is there. Now whenever you are choosing that the epsilon value to be 2, then x is falling inside a minus 2 and a plus 2. Now when you are choosing epsilon to be 1, then you are saying that this same x is falling between a minus 1 and a plus 1. When you are choosing epsilon to be 0.00001, you are saying that x is falling in bit here. X lies in the limit, in the interval a minus epsilon 0.0001 plus and a plus 0.001. So whatever value of epsilon you choose, it is falling always inside that point, okay, inside that interval. And if it happens, and if it goes on happening, then actually the point, this arbitrary point you are talking about, it is actually equal to a. So the proof is very easy, but it is there in the book, so you can see it from there. But you have to, I'll suggest not to go in details with these things, because it will just kill your precious time, and therefore just stick to what I say to you, and that will be much more for covering your syllabus. So these two definitions, neighborhood of a point and this theorem, they are actually too important, and you have to remember this always, okay. Another theorem, another definition I must write uh, uh, first of all, before I proceed to study mean value theorem, because sometimes in some definitions or in some theorems, these definitions will can have some sort of contribution. So therefore, this is point number 1 I wanted to discuss. This is point number 2 I wanted to discuss, and point number 3 is another definition which also you have to keep in mind. So the second definition I'm talking about is goes like this. Let capital A is a subset of R. Okay, a point C belonging to R, a point C belonging to R is a point C belonging to R is a cluster point, of A if for every epsilon, if for every epsilon, sorry, every delta greater than 0, there exist at least one point, there exists at least one point x belongs to A, x not equal to C, such that mod of x minus C is less than delta, or C minus delta less than x less than C plus delta. This definition is also very important. It's a definition of cluster point, and you won't believe from where I have selected this definition, from which chapter of the book. The chapter's name in the book from which the definition I'm writing is called limits. But unfortunately, when we have come across limit for the first time in school, cluster point was not defined. I'm pretty much sure. But in any school, if the teacher has defined cluster point, then he's a very good teacher. In the chapter of limit, in the very first page, the definition of cluster point is given. Okay, without understanding the cluster point, limit concept cannot be understood. Okay, anyways, we sometimes actually go with the symplectic way of teaching, and therefore these symplectic ways are often applied in schools, and therefore probably they have missed cluster points due to lack of time in for finishing the syllabus. So anyways, you have to know cluster point because you are in undergraduate course. So in the real line, the real set of real numbers, you are selecting a set capital A. Obviously, you know that capital set, this set capital A is kind of interval. Okay, because R is a line, and therefore if you consider any subset of that, it will be a kind of interval or a singleton, a set containing discrete points. It may contain a discrete point also, discrete real points also. Don't consider always this as a interval, a set of discrete points, or a singleton set, anything which is on the real line. A point C belonging to R is a cluster point of capital A if for every delta greater than 0. Again, delta has been considered over as positive because it counts distance, and strictly positive because if delta equal to 0, there is no point in discussing cluster points and neighborhoods. Okay, so if for every delta greater than 0, there exists at least one point, not at most, not exactly, at least. So this term is very important. At least one point x belonging to A, which will be different from C, such that the distance between that point and C will be lesser than that delta. So suppose if you want to see it, then I can say that, okay, suppose this is your real line, and you are considering an interval, sub interval like this, and here lies your point C. Here lies your point C, or very close to the end point. Now C will be the cluster point. Cluster point of what? not of the real line, cluster point of the set A. Now this is your set A, this is your set A, which is a subset of real line. So C will be the cluster point of A if there exists at least one point or more than that in A, whose difference, which is whose distance from C is actually less than delta. What does it mean? It means that if you consider any delta, any small interval, like this, any small, as small as you can make it, then a point from A will belonging to that interval. Or again, uh, for again, say I'm again writing this as another diagram I'm drawing. Now this is your C, this is your A, and this point is your C, say here, this is your C. So you can choose your delta so small that you are considering a delta neighborhood. I cannot draw it because it is so difficult. C minus delta and C plus delta. And if you can select such a neighborhood of C where you see that at least one point of A falls inside here, say X lies here in this interval, then you will say that okay, C is the cluster point of this particular set capital A. So analysis is always, the analysis is always, just a minute, okay, just a minute. Sorry for the interruption. Now because another class is going on besides, so actually that is that's why I was telling to close the door. Now analysis is always, you know, is kind of I mean, it is actually kind of, if you can imagine things, then in a better way, then you can imagine the analysis, you can do the analysis. Analysis is all about imagination, because we have to deal with those things in micro level, smaller level, micro level, and therefore it's always not possible for us to draw diagrams and to show you things. But you have to imagine. If your imagination is good, then you can deal with that. Say for example, the student who is learning how to count, then he has started his counting from childhood, and he goes like 1 2 3 up to, and at a certain point of time he has been asked that what is the largest number. Okay, then if the student is intelligent enough and his imagination power is good, then he will not answer the question at that point when he was first asked this question, and he will just move out of the room. But if the question is not careful, if the student is not careful enough, he may say, he may give you anything, he may give you that 1 lakh is the largest number. Okay, then you can tell him that okay, what about then 1 lakh plus 1. Okay, so imagination is very important over here. So you imagine, try to imagine what is cluster point. Okay, I can say up to this, then rest of the things you have to imagine, okay, to get a better idea of that. So with this prerequisites, let us move on to the discussion of mean value theorem. And let's start with although I have given the chapter 6, but I am starting from the part which is called the mean value theorem, that is section 6.2. And first of all, I'm going to write definition of relative maximum and relative minimum. Okay, so let us first write the definition. The function, okay, so my discussion is mean value theorem. Let us write it, mean value theorem. And the definition goes like this: the function f colon I to R, okay, is said to have a, is said to have a relative maximum at C belonging to I if there exists a neighborhood V of C such that fx is less than or equal to fc for all x in V intersection I. That is the definition of relative maximum. And the corresponding definition of relative minimum I am writing separately, just not as given in the book, so that you can understand it in a clear way, that function f colon I to r is said to have a relative minimum at C belonging to I if there exists a neighborhood V is equal to V of C such that Fc is less than or equal to Fx for all x in V intersection I. Okay, I am enabling the chat box so that you can put your attendance over there. So the countdown has started, so quickly give your attendance for the first session. At least I can say that you can find that whenever they have defined relative maximum and relative minimum, they have used the concept of neighborhood. So if the definition of neighborhood is not clear to you, if you are not acquainted with this notation V delta C, then we shall not be able to understand what the definition is actually saying. The definition is saying certain things which you can imagine diagrammatically, but mathematically, analytically, they have been written in the following way. So first of all, we have to dissect this particular statement carefully, and we have to understand each statement given over here. So I don't know whether I shall be permitted time in this particular session, but at least let me try, let me give it a try, and let me start discussing things in this particular session regarding these two definitions, and then we can carry forward in the next session. But again, I am saying that if you are impatient, then it's not, this calculus subject is not for you, because it will take some time. And it is you can ask, you can say to me that, sir, you said the same thing in case of linear algebra. So here the patience in this particular class, the patience level is much more higher than the patience level of linear algebra. Okay, so stay with me. One thing you can ask me, if you are careful reader, you can say that, sir, if whether this delta and that delta, they are same or not. Obviously they may be same or they may not be same. Okay, so these deltas are different, but in the book, when writer writes something, he wants to save space, and therefore they have written it in the same line. Okay, they have said that the way you can define relative maximum, the same way you can define relative minimum also. So therefore they have used the same symbol delta, but it is not that for an interval C minus delta and C plus delta, relative minimum and relative maximum together exist. It is not like that. Deltas are different, but you can consider the two definitions separately. So we have just used the symbol delta. to avoid the clumsiness. What is this? F is a function from I to R that I want to discuss a little bit, but as time is running out, so it would be much better for us to, if we start studying start dissecting this particular definition in the next session. Meanwhile, you can do one thing. You can draw two graphs in your copy quickly. One graph is called f of x square, f of x equal to x square. Another graph is called fx equal to mod x. Okay, then you can draw a graph fx equal to sine x like this. You can draw these graphs in your copy, and we can uh, start studying that in the next session. Okay, so I'm pausing the video right now, and let's wait for the next session to begin. Meanwhile, you try to understand, you read the definitions again and again, and try to understand what this definition is saying.